Hi, my name is Sergey Levin, and today I'm going to talk about offline reinforcement learning. So to start off, let's start with a big question. What is it that makes machine learning work today? And, I'm going to give a simple answer to the big question. This is going to be maybe somewhat controversial, but perhaps many of you will agree with this, at least at a very, very high level. I think that what makes machine learning work today is really the combination of large and highly diverse data sets and large and high-capacity models. And what we've seen time and time again is that across a range of domains, from image recognition to machine translation to text recognition and speech recognition, this kind of formula seems to be the formula that leads to good results. If you collect a large data set like ImageNet or MS COCO and then train a huge model with dozens or even hundreds of layers, that's going to be the thing that leads to very good performance. And arguably, the widespread enthusiasm about machine learning in recent years has really been spurred on by applications that follow this basic formula. So what about reinforcement learning? What about using learning to figure out how to make decisions? Well, reinforcement learning is fundamentally, at least in the textbook setting, an active learning framework where you have an agent that interacts with the world, collects some experience, uses that experience to update its model, policy, or value function, and then collects more experience. And this process is repeated many, many times. And we've seen that this basic recipe does lead to good results across a range of domains, from playing video games to basic robotic locomotion and manipulation skills, and even to playing the game of Go. However, when you want learning systems that generalize effectively to large-scale real-world settings, like the ones that I showed on the previous slide, you still have to collect large and diverse data sets. And in an active learning framework, this means that each time the agent interacts with the world, they need to collect a breadth of experience that covers the sorts of situations they might see in the world. For example, if you imagine using reinforcement learning to train an autonomous driving system, now this system might need to practice driving in many, many different cities each time it updates the model. So it goes and drives in San Francisco, New York, Berlin, London, updates the model, and then goes back to San Francisco, New York, Berlin, and London. Now this very quickly becomes impractical. And indeed, if we look at the kind of domains in which modern reinforcement learning algorithms have been successful, and then contrast it side by side with the kind of domains where we've seen the success of supervised learning methods that can leverage very large and diverse data sets, we see that there's a really big gulf. It's not that the reinforcement learning algorithms are not capable. They're learning very sophisticated strategies, very sophisticated behaviors, but they're not exhibiting the same kind of open world generalization. All of the domains that I'm showing on the left can all be characterized as closed world settings. We know exactly what the rules of Go are. We know how the emulator for the video game works. Even the robotics application is in a laboratory setting. Whereas all of the applications shown on the right are open world domains. Images mined from Flickr from all over the world, natural text, natural speech collected from real human beings actually speaking or writing text in the real world. So if we want to bridge this gulf of generalization, what can we do? How can we bring reinforcement learning into these open world settings to address the kind of applications that we actually want? Well, I'm going to posit that in order to enable this, we really need to develop data-driven reinforcement learning methods. And data-driven means that you need to be able to use large and diverse previously collected data sets in the same way that supervised learning algorithms can utilize large and diverse previously collected data sets. The classic textbook version of reinforcement learning is really an on-policy formulation. In an on-policy reinforcement learning algorithm, you have a setting where each time the agent updates its policy, it has to go and collect new data. A very common area of study in reinforcement learning is also to study off-policy reinforcement learning algorithms. And these algorithms can utilize previous data, but they typically still learn in an active online fashion, meaning that the agent interacts with the world, collects some data, adds that data to its buffer, and then uses the latest data and all past data to improve its policy. And we might think that we could simply cut that connection, we could simply use prior data using the same exact algorithms, but as I'll discuss in today's talk, that actually doesn't work very well. And if we really want data-driven RL algorithms, then we need to come up with some new algorithmic techniques to make this possible, and develop a new class of what I'm going to call offline reinforcement learning methods. These have also been called batch reinforcement learning methods in the literature. The idea here is that a dataset was collected previously with some behavior policy that I'm going to note pi beta. In general, you might not even know what pi beta was. Maybe it was a person driving a car, a person controlling the robot. Maybe it was the robot's own experience on other tasks. Whatever it was, it collected a buffer of data, a large and diverse data set that covers many different open world situations. And now you have to learn the best policy you can for your current task using just that data, without the luxury of interacting with the world further to try out different methods. Now, of course, in reality, we might want something that more like a hybrid. In reality, maybe what we have is we have a big data set from all the past interactions that our agent has had. Maybe you have a robot that has cleaned the kitchen and mopped the floors and did many other things. And that's sort of its foundational data. It's ImageNet style data set that it's going to use to get generalizable skills. We're going to use that data set in an offline RL fashion. And then perhaps we'll actually come back and interact with the world a little bit more just to fine-tune that skill, just to collect task-specific data in small amounts. And I'll actually discuss some methods that can do this as well. But the main component, the main challenge of this recipe is really the first part, is using large and diverse previous data sets to get the best policy you can without having to revisit all those diverse and varied situations, without having the car go back and drive in San Francisco and New York and Berlin and London each time its policy changes. And if we can accomplish this, if we can build algorithms that have this capability, then we will not only be able to train better policies for robots and things like that, but we'll also be able to apply reinforcement learning to domains where conventionally it has been very difficult to use. For instance, we could imagine using past data to use reinforcement learning to train a policy for advising doctors on treatment plans and diagnoses. It would be pretty crazy to imagine an active exploration procedure for doing this, because that would result in enormous cost and liability. But if you can use previously collected offline data to get the best decision-making system you can to support doctors in a medical setting, well, that seems like a pretty good recipe. You could imagine the same procedure being applied to scientific discovery problems, controlling power plants, chemical plants, operations research, logistics and inventory management, finance. In all of these domains, there's ample previously collected historical data, but it's extremely difficult and costly to run active online data collection. So we would expect that these would be the domains that could be revolutionized with effective offline reinforcement learning algorithms. So in today's talk, I'm going to cover the following topics. First, I'll discuss why offline reinforcement learning is difficult. Then, I'll talk about some basic recipes for designing offline RL algorithms and a little bit about recent progress in this area. I'll talk about some of our recent work on model-based offline RL. And then I'll discuss a new algorithm that we're pretty excited about called conservative Q-learning, which seems to be a way to do offline RL that works quite a bit better than many of the previous methods. And then I'll conclude with a discussion of how we should be evaluating our offline reinforcement learning algorithms and discuss a benchmark that we've developed recently called D4RL. All right, but let's start with the first topic. Let's talk about what makes offline reinforcement learning hard and why we can't use our standard off-policy RL algorithms to solve it. So first, let's start with a quick primer on off-policy reinforcement learning. In a standard reinforcement learning problem, you have an agent that interacts with the world by selecting actions, and the world responds with states and the rewards, the consequences of those actions. What the agent needs to do is select a policy, which I'm going to denote as pi of a given s. And that policy needs to be selected so as to maximize the reinforcement learning objective, which is the sum of expected rewards over all time. So the agent doesn't just take the action that yields the highest reward right now, it's supposed to take the action that yields the highest rewards in the long run. Now, a very useful object for maximizing this reinforcement learning objective is the Q function. The Q function tells you if you start in a particular state, take a particular action, and then follow your current policy pi, what is the total reward that you will accumulate? And if you can somehow determine the Q function for a given policy, then you can always improve that policy by taking an action with probability 1 if it is the argmax of the Q function and 0 otherwise. So this greedy policy with respect to q pi will always be at least as good or better than the previous pi. And you can also skip the middleman and directly enforce the Bellman optimality equation for all state action tuples. So if you can make QSA equal to RSA plus the max of the Q value at the next time step, then you can also show that recovering the greedy policy from this will get you the optimal policy. And one way you could do this is you could enforce this equation at all states by minimizing the difference between its left-hand side and right-hand side. Now, this is all fairly basic stuff. This is kind of what we learn, when we first learn about reinforcement learning. It's textbook RL. But, as many of you might already know, the nice thing about this equation is that you don't necessarily need on-policy data to enforce it. Now, this talk is going to focus pretty much entirely on approximate dynamic programming methods, basically Q-learning style methods or actor-critic methods. There are many other methods for offline RL based more around policy gradient style estimators. And I'm not going to talk about this, so we'll basically start with Q-learning and actor-critic and sort of stay there, just as a warning. Okay, so this procedure that I've laid out here, this classic Q-learning approach, is an off-policy algorithm, which means that you don't need on-policy data to make the left-hand side and right-hand side of the Bellman optimality equation equal to each other. So you could imagine an off-policy Q-learning method or a fit Q iteration procedure that has the following basic recipe. This is sort of classic stuff from literature. Collect a data set of transitions using some policy, add it to a buffer, sample a batch from that buffer, minimize the difference between the left-hand side and right-hand side of the Bellman optimality equation, and then repeat this process some number of times. And then periodically you could go out and collect more data. You could also think of this graphically. You interacted with the world, collected a data set of transitions, you're going to run your Q-learning procedure on that data set, and then periodically go back and explore. And of course, if we're doing offline RL, then this is the part that we would omit. We would just take our buffer and just keep crunching away with Q-learning on that buffer. So this is an off-policy algorithm, and it can accommodate previously collected data in principle. So does it solve the offline RL problem? And if not, what goes wrong? Well, we studied this question a little bit, so what I'm going to show next is some results from a large-scale reinforcement learning project that we actually did at Google a couple of years back called Qt-opt. Our goal in this project is to develop a highly generalizable and powerful robotic grasping system that could learn to grasp any object directly from raw images. But in the process of doing this research, we actually evaluated a little bit how these Q-learning style methods compare in the fully offline regime versus the regime where they're allowed to collect additional online data. Now, here, there's, everything is kind of scaled up, so there are 7 different robots that are all collecting lots of data in parallel. They're pushing it to a decentralized distributed buffer, storing all the data from past experiments, and there are multiple workers that are actually updating Q values on everything in the buffer. We looked at how the system worked. It actually worked really well. It could pick up novel objects, heavy objects, awkward objects. It could respond to perturbations that it had never seen before. So basically, when we scale up reinforcement learning, it does actually generalize. Something is really working, and we're seeing generalization that kind of resembles the kind of open world generalization that we saw in the supervised setting. Of course, here one might argue it's not entirely open world, it's still in the laboratory, but it is generalizing to never before seen objects. So we evaluated this method on a test set of objects that the policy never saw during training. We actually bought entirely new objects just to ensure that they were not in the lab during the training process. And then we compared the algorithm trained in fully offline mode, meaning using just the data you collected before, trainable policy, and then see how it does. And this was fairly good offline data. It came from past RL experiments. And we also evaluated the algorithm in fine-tuned mode, where the policy was allowed to collect a little bit of additional data and fine-tune online. The offline dataset consisted of 580,000 episodes, so this is a very large grasping episode. The online fine-tuning added another 28,000. So the amount of additional online data was pretty negligible. So it was clearly not the increase in the dataset size, it was really that it was online. And we saw the following numbers. The success rate was 87% for the offline method, and 96% with the additional online fine-tuning. And while this might seem like a small difference, if we rewrite this as error rates, we have an error rate of 13% for the offline method and 4% for the fine-tuned method, so less than a third of the number of mistakes. That's a pretty big difference, actually. So the system clearly works very well, but you're getting 3 times fewer mistakes if you fine-tune with even a small amount of data. So something about the fully offline setting seems to be pretty hard. Now, more recently, we actually studied this question in a paper called Stabilizing Off-Policy Q-Learning via Bootstrapping Error Reduction by Aviral Kumar, Justin Fu, George Tucker, and myself. And we wanted to understand what are the reasons why this might be so difficult. We had a few hypotheses that we wanted to investigate. One hypothesis we had was maybe there's some kind of overfitting effect. Maybe when you train on offline data, if you train too long, you sort of overfit to that data and you start seeing bad performance. But if it was an overfitting effect, then what we would expect is that increasing the dataset size should decrease the problem. So what this plot shows is offline RL performance on the half-cheetah benchmark, and different colors denote different datasets. So blue is 1,000 transitions, and red is 1 million transitions. And you can see that there is virtually no difference between 1,000 and 1 million. So if there is an overfitting effect, it is not the conventional kind of overfitting. It doesn't seem to go away as you add more data. Now, we also looked at how well the Q function thought it was doing. Meaning, if you actually look at the Q values for the current policy, that tells you how well the Q function thinks it's going to do when it's executed in the world. And this is a plot showing that. Now, something to note here is that the y-axis here is actually a log scale. So what this is showing is enormous overestimation. Actual performance is below 0. Estimated performance is between 10 to the 7th and 10 to the 20th power. So the Q function thinks it'll do extremely well, and it is doing extremely poorly. Well, that's kind of weird. Another hypothesis we had is, well, maybe the trouble is just the training data is just not good. Like, maybe the best you can do with this data is minus 250. Now, one way that you can evaluate that hypothesis, you can actually look at the best transitions in the data set. If you just copy the best transitions, how will we do? We'll actually do pretty well. So this is usually not the case in these offline RL problems. It's not that the training data doesn't have good behavior, it's that somehow the Q function becomes excessively confident and optimistic about actions that are not actually very good. To understand what's happening here, we first have to understand distributional shift. So here's distributional shift in a nutshell. When we run supervised learning, we're typically solving what's called an empirical risk minimization problem. So we have some data distribution P of x, we have some label distribution P of y given x, our training set consists of samples from P of x and P of y given x, and then we're going to minimize some loss on those samples. And if we're doing Bellman error minimization, then we're minimizing the squared error between the values predicted by our function f theta and the target values y. Now, when we run empirical risk minimization, we could ask the question, given some new data point x star, is f theta of x star going to be correct? Well, one thing that we do know is if we had enough samples, then the expected value of the error under our training distribution should be low. That's what generalization means. Generalization means that training error, which is the empirical risk, is representative of generalization error. If you have a large training set, minimizing training error is going to minimize generalization error unless you overfit. But that doesn't necessarily mean that we're going to make an accurate prediction on some other point x star. For example, the expected value of our error under some other distribution over x, p bar of x, is not in general going to be low unless p bar of x is equal to p of x. So our error under a different input distribution might be, in fact, very high. In fact, even if x star was sampled from p of x, we're not guaranteed that error on x star is low because we're minimizing expected error. So we might still have some points with high error. We're not minimizing pointwise error, just expected error. Now, you might say that usually when we train deep neural networks, we're not too worried about this kind of distributional shift because deep networks are really powerful. They generalize really, really well. So maybe it's okay. But what if we select x star so as to maximize f theta of x? See, we might have a function that fits the true function really well. Let's say that the green curve represents the true function and the blue curve represents our fit. Mostly our fit is extremely good. However, if we pick the largest value of f theta of x, which point are we going to land in? Well, we're going to land exactly on that peak. We're going to find the point that has the largest error in the positive direction. So even if we're generalizing really, really well, even if we're doing well for x star points, even ones outside of the distribution, if we maximize the x, we're going to get big errors. So what does this have to do with Q-learning? Well, let's look at our target values in Q-learning. It's r of SA plus the max over A prime of Q of S prime comma A prime. And I'm going to rewrite this in kind of a funny way. I'm going to write this as r plus the expected value of A prime under the policy pi nu, where pi nu is this argmax policy. So pi nu assigns the probability of 1 to the argmax. Now, this is kind of just a really weird way of writing the max, but I think it makes the distributional shift problem much more apparent. So let's say that our target values are called y. What is the objective for the Q function? Well, it's to minimize the empirical risk, the empirical error against y, under the distribution over states and actions induced by our behavior policy pi beta, which means that we would expect Q to give us accurate estimates of Q values under pi beta. Right? Pi beta is the behavior policy. So we expect good accuracy when pi beta is equal to pi nu. So if pi nu is pi beta, then we're fine. We're going to have low error estimates. But how often is that true? Pi nu is chosen to maximize the Q values. So unless pi beta was actually also maximizing those same Q values before it even knew what they were, these things are not going to match. And it's even worse. Pi nu is selected to be the argmax. And if you think back to the previous slide, when you select your point with a max, you get some bad news. And that's why we see on these half-cheetah experiments that the policy does poorly, whereas the Q function thinks it's doing really well, because it's finding the actions with the largest error in the positive direction. And that's why just naively applying off-policy RL methods to the offline setting does not in general yield great results. So we have to somehow combat this overestimation issue. We have to combat the distributional shift in the action space. So let's talk about how we can do this. How do we design offline RL algorithms? Well, one very large class of methods in the literature, and this is summarized in a tutorial that we assembled recently called Offline Reinforcement Learning, Tutorial Review and Perspectives on Open Problems. One very large class of methods is what we're going to call policy constraint methods. So it's easiest to describe policy constraint methods in the actor-critic setting, but they can be applied in the Q-learning setting too. So here we're going to update our Q function just like before, using the expected value under pi nu. And then we'll update our policy not just by taking the argmax, but by taking the argmax subject to a constraint that some measure of divergence between pi nu and pi beta is bounded by epsilon. So the idea is that if pi nu stays close to pi beta, then the distributional shift will be bounded, and therefore the effective out-of-distribution actions will be bounded. And then you repeat this process. So it's just like an actor-critic algorithm, only with this additional constraint against the behavior policy. So does this solve distributional shift? Does it mean that we have no more erroneous values? Well, to a degree it actually does. So there is a pretty large class of methods that have explored various kinds of policy constraints. It's in a sense a very old idea. We coined the term policy constraint, I think, in our tutorial, but these kinds of approaches have been called many things in the literature, including KL divergence control, maximum entropy RL, linearly solvable MDPs, all sorts of things. And there are many researchers that have studied this for decades, not just in the offline RL literature, but in the RL literature more broadly. More recently, this has been used extensively for various off-policy and offline RL methods. Here is just a collection of recent citations, kind of from the last 5 years, that have done some variant of this. Now, this does have a number of problems. One problem is that this kind of approach might be way too conservative. Imagine the following scenario. Let's say that you have a behavior policy that is highly random in some places and almost deterministic in other places. Now, when the behavior policy is highly random, you actually get pretty good coverage of actions, and the effect of out-of-distributions is actually minimized. In fact, if the behavior policy was uniformly random, nothing would be out of distribution because it has full support. But if you have a policy that is highly random in some places and highly deterministic in others, it's actually very difficult to pick a value of epsilon that works. Because if you pick a value of epsilon that is too low, then in the places where the behavior policy is highly random, you'll be able to do all sorts of interesting things in its support. But in the places where it's not highly random, you might take a really bad action. Right? So imagine it's kind of close to deterministic when it's crossing a narrow bridge, where with some small probability it falls off. If you admit that amount of error, you might fall off the bridge. If you use a tighter constraint, if you limit the amount of deviation from the behavior policy very strictly, then you won't fall off the bridge. You'll match it in that highly deterministic region, but you'll also be forced to match the highly random distribution in the region where it's random, and that's just useless, right? If the policy is being very random, being just as random doesn't seem to give you anything. Like if it's random, you can just choose within that support whatever you want. So it's hard to pick a single value of epsilon that works better. Now, one thing that can mitigate this is to use a support constraint. To basically say, it's not that you have to match the distribution, you just have to match the support of that distribution. So if the distribution is highly random, you can do sort of anything you want within that support, but if it's highly deterministic, you really need to do whatever it did because you don't have any wiggle room to go out of support. And we explored this a little bit in a paper from 2019 that introduced an algorithm called BEAR, which uses support constraint. The second issue, which is a bit tougher to deal with and actually pretty problematic in practice, is that estimating the behavior of the behavior policy itself in order to enforce this constraint can be very difficult. If you don't know what the behavior policy was, maybe the data was collected by a human, you have to somehow figure out what policy that human was following, and if you make a mistake in figuring it out, then your constraint might be incorrect. So for example, if you fit the behavior policy with supervised learning, we know that supervised learning will make certain mistakes. It has kind of a moment matching effect, which means that it will average across modes, which means you might have high probability actions under your behavior policy that had a very low probability under the true behavior policy. And when you enforce a constraint against that, the constraint will be highly imperfect. And this can lead to very poor performance in practice. Now, when is estimating the behavior policy especially hard? Well, it's especially hard when the behavior policy actually consists of a mixture of multiple different behaviors. And this is actually exactly the setting that we want, because remember, I motivated all of this by talking about the setting where you have a large and highly diverse data set. And that's exactly when you would expect that your behavior policy would actually be a mixture of many different policies. And at that point, estimating it with a single neural network is actually very hard. So the easy case is when all the data comes from the same Markovian policy, but this is not very common or very realistic. If your data came from humans, they're certainly not going to be Markovian. If it came from many past tasks you've done, while each individual task might be Markovian, the mixture might not be. So the hard case is where the data comes from many different policies, and this is very common in reality. And it's also very common when you're doing online fine-tuning. So if you remember when I motivated all this, I also said that we want to collect lots of data from past behaviors, train a policy with offline RL, and then maybe fine-tune it further with a little bit of online data. So let's use this online fine-tuning as a kind of test case. In reality, what we care about is the setting where data comes from many different policies, but the online fine-tuning situation is a nice sort of petri dish in which to explore this problem. So I'm going to talk about a method that we've developed that specifically targets that setting, where first you have offline training on a large previously collected data set, and then you have some online fine-tuning. And during online fine-tuning, you're adding more data from many different policies. So this is work by two of my students, Ashwin Nair and Abhishek Gupta, together with an undergraduate student named Murtaza Dalal. So the experiment is that we do online fine-tuning from offline initialization. And what I'm showing in this plot is the log likelihood of the behavior policy fit. So this is for one of these standard policy constraint methods, in this case BEAR. And the left side shows the offline training, so you can see during offline training we get pretty good log likelihood for fitting our behavior policy. But during online training, when we have these additional samples from many different policies being pushed to the buffer, the likelihood of the policy estimate drops precipitously. It drops very sharply for the online data, and it even drops for the old offline data because you have to also model the new offline data, so you do worse on the offline data. So our fit gets bad. And in fact, we can see that this method, this is BEAR, but this would be true, I think, for most policy constraint methods, doesn't do so well. So this is just showing the online fine-tuning, and you kind of have two choices. You can use a strict constraint or a loose constraint. If you use a strict constraint, then you do a little bit better at the beginning, that's the yellow line, but you fail to improve because as the behavior policy deteriorates, that strict constraint just basically causes everything to get stuck. If you use a loose constraint, then you improve over the course of online training, but you start off in a really bad place, and in this case, it's no better than just initializing from scratch. And in fact, this general principle is borne out in a few other papers. For example, this paper I have cited here called MOPO shows that using a much more powerful class of behavior policies leads to substantial improvement, implying that behavior policy modeling is really a major bottleneck for these policy constraint methods. So one of the things we could do is we could actually enforce a constraint without explicit modeling of the behavior policy. So this is a kind of implicit constraint method. So here's the idea. The problem we want to solve is this constrained argmax. It turns out that you can prove that the solution to this constrained optimization problem can be expressed in closed form, and the way that you do this is you write down the Lagrangian, solve for the dual, and then you can actually write down the optimum for the dual. And the optimal solution is given by 1 over z times the behavior policy times the exponential of the advantage function. And the advantage function is multiplied by 1 over lambda, where lambda is a Lagrange multiplier. And this is straightforward to show using a duality argument. We didn't actually come up with this. This has actually been brought up in a number of previous papers, including the REPS papers by Peters et al., the Rawlik et al. Sci-learning paper, and many others. This is kind of actually a very well-known identity in Kale regularized control. But the interesting thing about this equation is that it shows that we can approximate the solution to the constraint optimization using a weighted maximum likelihood objective. And the way to do this is to note that matching this pi star is the same as maximizing the likelihood of actions taken from pi star. And you can do that by taking actions set from pi beta and weighting them by the exponentiated advantage. So if you can find the argmax of the expression I have written here, then you will get pi star, provided that you can match pi star exactly. And the cool thing about this expression now is that pi beta only shows up as the distribution in the expectation. So even though you need pi beta for this, in reality all you actually need is samples from pi beta, which means that you do not need to actually know the distribution pi beta. And samples from pi beta, that's exactly what our dataset is composed of. So we no longer need to estimate the behavior policy, we just need samples from it, and our dataset already contains those. And of course the advantage we get from our critic. So you could imagine an actor-critic algorithm which updates the critic to get the advantages and then updates the policy using this weighted maximum likelihood expression. All right, so does this procedure work? Well, if we look at some results from the paper, we evaluated on these kind of dexterous manipulation tasks where we had a data set from human demonstrations with a data glove. And then if you look at what those human demonstrations do, they get a success rate of about 24% on this door task. With some online fine-tuning, you get an 88% success rate. So this is doing much better than if you were to just copy the demonstrations, and you get meaningful fine-tuning. Now, of course, this is an offline RL method, so it doesn't actually need demonstrations per se. That's just what we had in these experiments. We had other experiments that also used random data. Quantitatively, the method actually does really well. It's shown by this red line here. The pen task is the easiest, the door is kind of medium, and the relocate task is the hardest. And you can see that as the tasks get harder, this method, denoted as AWAC, ends up doing the best. So it kind of matches previous work on the easy task and then greatly exceeds it on the harder tasks. So this shows that something is really working with these implicit constraints. All right. Now let me take a little detour to delve a little bit into the world of model-based reinforcement learning, because we can also develop effective offline RL algorithms in the model-based world too. So just a brief overview of model-based RL, for those of you that aren't familiar with it. In model-based RL, what we're going to do using data that we collect from the environment is we're going to fit a model. We're going to fit an estimate to the transition probabilities, p hat of st plus 1 given st comma at. And then we'll somehow use that model to train a policy pi of at given st, and then typically repeat the process. So one way that you could imagine such a model-based RL algorithm working, and this is sort of a DINA-style recipe, is that you collect real data, denoted by these black trajectories. You use that real data to fit your model, and then you're going to use that model to make kind of little short rollouts from different states in your data set. And these little short rollouts will be on policy using your latest policy. So the model kind of answers these what-if questions. If I were in the state that I had seen before, what would have happened if I took a different action? And this, of course, lets you train your policy much more efficiently. And of course, in offline RL, we're going to omit this error. We're not going to allow the algorithm to collect more data. It has to content itself with the data that it already has. So what could go wrong? Well, as you might have already guessed, the problem again is going to be distributional shift. When we make these rollouts under the model, if the policy that we're now evaluating is very different from the policy that originally collected the data, rolling out the model under that policy will result in state visitations that are very different from the states under which the model was trained, and the model will make very large mistakes. And of course, since the policy is again being trained to maximize the return, it'll learn to exploit the model to essentially cheat so that the model erroneously produces good states. Now, in the literature, one of the ways that people have mitigated this effect is by just shortening these rollouts. So if you don't allow the policy to roll out for very many steps under the model, there's only so much exploiting that it can do. But in the fully offline setting, of course, you don't want to do this because your policy might deviate drastically from the behavior policy, so you want to give it longer rollouts so you can actually tell how well it's doing. So the model's predictions will be invalid if you get these out-of-distribution states. Very much like the problem we saw before. So one solution we've developed, and this is joint work with Tianhe Yu and Garrett Thomas, who are the co-first authors, as well as a number of collaborators. Most of the team here is from Stanford University, led by Professors Chelsea Finn and Tengyu Ma. And there's also some concurrent work by Kadambi et al. That also propose a very closely related algorithm called moral. But I'm going to talk about our paper called MOPO. So the solution is to basically punish the policy for exploiting these out-of-distribution states. So what we're going to do is we're going to take our original reward function and we'll subtract a penalty with a coefficient lambda. And this penalty u is essentially going to be some quantity that is larger for states that are more out of distribution, or state action tuples that are more out of distribution. So it's a kind of uncertainty penalty. And that's the only change we're going to make. We're just going to change our reward like this, and then use some existing model-based RL algorithm. The one that we used in MOPO is based on an algorithm called MBPO, Model-Based Policy Optimization. So the idea now is when you visit one of these out-of-distribution states, you get a really big penalty. And that results in the policy not wanting to visit those out-of-distribution states and instead curving back to the support of the data. Okay, so there's some pretty interesting theoretical analysis that we can do for this algorithm. And the theory, this is kind of the statement from the main theorem in the paper, which states that under two technical assumptions, the learned policy pi hat in the MOPO algorithm satisfies the property that the return of pi hat is greater than or equal to the supremum over pi of the return of pi minus 2 times lambda times epsilon u. Okay, so what are all these things? There are two technical assumptions. One is that we can basically represent the value function, so things will break down badly if you have really bad function approximation error. And the second one is an assumption on u, which says that the true model error is bounded above by u. So this is essentially saying that u is a consistent estimator for the error in the model. And you need this property basically because you need u to mean something. In practice, the way that we estimate mu is by training an ensemble of models and measuring their disagreement, but any estimator that upper bounds the error in the model will do the job. So this is the true return of the policy trained under the model, so not the return the model thinks it has, but the return it actually has. And epsilon here is just the expected value of u. So what this is saying is that the true return of a policy we optimize under our model will actually be at least as high as the best policy that still has to pay this error price. Another way of saying that it will be at least as good as the best in-distribution policy. Of course, you can't get the optimal policy because you don't know what happens out of distribution, but you can at least hope to do at least as well as the best in-distribution policy. Another way of saying this is that you can construct this policy pi delta, which is the best policy whose error is bounded. Basically, the best policy that doesn't visit states with error larger than delta. So this is under the true MDP, but it's saying you're going to find the best policy under the true MDP that doesn't visit states where the model would have made mistakes. And this result says that The policy we learn with model-based RL will be at least as good as that policy minus an error term that scales as 2 times lambda times delta. So this basically shows that we'll get a good policy within the support of our data. So some implications of this. This means that we always improve over the behavior policy, and we can actually quantify the optimality gap against the optimal policy in terms of model error. So basically, if our error on the state so that the optimal policy would visit is small, then we will get close to the optimal policy. Empirically, this method does very well. It outperforms regular MBPO. It also outperforms quite a few of the previously proposed policy constraint methods. All right, so now let me discuss the last algorithm I'm going to cover, which is called conservative Q-learning. Conservative Q-learning takes a slightly different approach to offline RL from policy constraint methods. So just to remind you, the problem we saw before is that the Q function kept thinking that it's going to do much better than it's actually going to do. So it's going to overestimate like this because when we take the R max, we get the point with the largest positive error. So instead of trying to constrain the policy, what if we try to directly fix the problem? What if we directly push down on erroneously high Q values? One of the ways we could do this is we can formulate a Q-learning objective with a penalty. So we have the usual term which says minimize the Bellman error, and then we have a penalty term which says pick the actions with the high Q values and push down on those Q values. So minimize the Q values under this distribution mu, which is chosen so that the Q values under mu are high. So this will basically find these erroneous positive points and push them down. It turns out that with this very simple regularizer, we can actually prove that the Q function we learn is a lower bound on the true Q function for the policy pi, if you choose alpha, the weight on the regularizer, appropriately. That's pretty cool. We're actually guaranteed not to overestimate if we do this. So this is work that was primarily led by my student Aviral Kumar, and the particular algorithm that Aviral proposed is a kind of actor-critic style algorithm where you learn this lower bound Q function for the current policy so that Q hat is less than or equal to Q, and then you update your policy. Now, you don't actually need to represent the policy exactly. It's just a little explicitly. You can still have a Q-learning algorithm where it's implicit, where it's the argmax policy, but it's a little easier to explain in an actor-critic setting. We call this conservative Q-learning, though, because it's also very simple to instantiate as a Q-learning method. Now, you can also derive a much better bound for conservative Q-learning. The bound I had on the previous page was actually too conservative. It actually pushed down the Q values too much. What you can do is you can push down on the high Q values, but you can compensate by also pushing up on the Q values in the data set. So you push down on the Q values that the Q function thinks are high, and then you push up on the Q values for the actions in the data set. Intuitively, what this means is that if the high Q values are all for actions that are in the data set, then these two terms will cancel out and the regularizer goes away. So when you're in distribution, there is no regularization. If you go more out of distribution, you get more regularization. So these are the two error terms: push down on actions from U, push up on actions from D, from the data set. Now, you're no longer guaranteed to have a bound for all state action tuples if you do this, but you are, turns out, still guaranteed to have a bound in expectation under your policy. So the expected Q value under pi for Q hat will still be less than or equal to the expected value under the true Q function for pi for all the states, provided that alpha is chosen appropriately, of course. So the full bound, the full conservative Q-learning algorithm is shown here. You minimize the big Q values and you maximize the Q values under the data. The full bound is written out here. So the left side is the estimated value function. It's less than or equal to the true value function minus a positive pessimism term due to the regularizer. And then there's this error term that accounts for sampling error. So you just have to choose alpha so that this positive pessimism term is larger than the positive sampling error term. Obviously, if you have more data, then your sampling error is lower, and you don't have to worry as much. If you have high sampling error, then you need a higher alpha to be conservative. Okay, so does this bound hold in practice? One of the things we did is we actually empirically measured underestimation versus overestimation on a simple benchmark task. So what I'm going to be showing is basically the expected value of the learned Q function Q hat minus the expected value of the true Q function. So if these values are negative, that means that Q hat is less than Q in expectation. If they're positive, that means we're overestimating. And we get the true Q function by actually rolling out the policy many times and using Monte Carlo. So here are the results. So the first column shows this the full CQL method with both the minimization and maximization term. The second column shows just the basic method that has just the minimization but no maximization. Then we have 4 different ensembles, so an ensemble of 2 networks, 4 networks, 10 networks, and 28 networks. And then we have BEAR, which is a representative policy constraint method. Now the first thing that you might note is that all of the ensembles and the policy constraint method are overestimating massively, despite the policy constraint. The simple CQL method that just has the minimization is underestimating, but by quite a lot. So rewards here are on the order of a few hundred, so getting minus 150 means that you're very heavily underestimating. Whereas the full CQL method underestimates, but only by a little bit. So we do have a lower bound, and the lower bound is pretty good. So the CQL always has negative errors, which means that it's pessimistic. All right, now before I tell you how well CQL actually does empirically, I want to talk a little bit about how we should evaluate offline RL methods. So how should we evaluate them? Well, ultimately what we're going to want to do is train our offline RL methods using large and highly diverse data sets. But in the meantime, when we're just prototyping algorithmic ideas, we need to somehow collect some data to set up a benchmark task. So maybe one thing we could do is we could collect some data using some online RL algorithm and then use it to evaluate offline RL. This is actually pretty typical in prior work. You train PyBeta with online RL, and then you either collect data throughout training or you take data from the final policy. I'm going to claim that this is a really bad idea, that this is a really terrible way to evaluate offline reinforcement learning methods, and if you're doing research in offline RL, you should not use data sets that have just this kind of data. Because if you already have a good policy, why bother with offline RL? But perhaps more importantly, in the real world, that's not what your data is going to look like. Your data is not going to come from a Markovian policy. It's going to come from humans, from many different sources, from your past behavior. It's going to be multitask. It's going to be diverse. It's not going to look like the replay buffer for an online RL run. So human users, hand-engineered policies, etc. So if you really want to evaluate your offline RL method, you really have to use data that is representative of real-world settings and leaves plenty of room for improvement. And then offline RL is to learn policies that are much better than the behavior policy, that are better than the best thing in your data set. Without testing for these properties, you can't really trust that our offline RL algorithms are good. And of course, in past work from my group, we've also been guilty of doing this, but we're mending our ways. We're not going to do this anymore. So we developed a benchmark suite called D4RL. It stands for Datasets for Data-Driven Deep RL. This was led by my student Justin Fu, together with Aviral Kumar, Ophir Nachu, and George Tucker. D4RL is actually rapidly picking up. It's rapidly becoming the most popular benchmark for offline RL because it really exercises the kinds of properties you want in offline RL algorithms. So what are some important principles to keep in mind? Well, you want data from non-RL policies, including data from humans. So we included things like the dexterous manipulation data that I showed before. This was based on data collected by Arvind Rajaswaran and colleagues. You want to evaluate whether your algorithm can put together different parts of different trajectories. We call this stitching. So if you've seen, for example, that you can go from A to B, and you've seen that you can go from B to C, but it's more optimal to go from A to C, the data actually tells you everything you need to know to figure that out, so you should be able to do this and do better than the best trajectory in the data set. So we evaluate this using some maze navigation tasks, both in a simple low-dimensional 2D setting and a complex setting where you have to have a simulated four-legged robot actually walk through the maze. So you never see full paths from the start to the goal, but you see paths between different places in the maze in your dataset. And you also have to have realistic tasks. We included first-person driving data from images using the Carla simulator, data manipulating objects in a kitchen from a paper by Abhishek Gupta called Relay Policy Learning, and traffic control data from Professor Alex Bynes' lab that simulates the effect of autonomous cars on traffic. So the set of D4RL tasks includes the standard Mujoko gym tasks with some difficult data sets, these stitching tasks in the mazes, dexterous manipulation tasks with data from real humans, robot manipulation tasks in this kitchen environment, again using human data, traffic control data from the flow simulator, and image-based driving in Carla. Now, if we look at how CQL compares on this benchmark, first let me show you the prior methods. One of the things to note is on the harder benchmark tasks, we actually see that, first of all, nothing works on the harder stitching tasks. So on the larger mazes, previous methods basically don't learn anything. These scores are all normalized between 0 and 100. The most competitive baseline across all of these harder tasks is just simple behavior cloning, which suggests that previously proposed offline reinforcement learning methods, which have primarily been tested on data from other RL policies, are not actually doing very well. So nothing beats behavior cloning on these harder tasks. If we look at the performance of CQL, it achieves state-of-the-art results on nearly all of these tasks. So I'm showing two variants of CQL, and one of these two variants is the best on all but one of the tasks, or tied for the best. So it's up to 5 times better on the harder dexterous manipulation tasks, 50 to 300% better on just the human data, 10 to 30% better on the kitchen tasks, and essentially infinitely better on the larger mazes, where it's the only algorithm that's able to exhibit the stitching behavior. We also evaluated the method on Atari data from a paper by Agrawal et al., and we saw there also that CQL is 50 to 600% better than previously proposed algorithms. So this method is doing really well. It seems to work quite well across many tasks. And we seem to know why it works, because of this lower bound property. Of course, there's still plenty of room for improvement, so if you want to develop better offline RL methods, there's plenty of work to do and plenty of ways in which you could improve the results. All right, so just to wrap up and conclude, I talked about how offline RL is quite difficult, but has enormous promise, and initial results suggest that it can be extremely powerful. I talked about how effective dynamic programming offline RL methods can be implemented by imposing constraints on the policy, and perhaps implicit constraints can get around the need to model the behavior policy. And I talked about how this learning a lower bound on the Q function using conservative Q learning can substantially improve offline RL performance. Thank you very much.